Gravity binds a family of 12 stars into a single, chaotic dance. This is a duodecuple star system, and its existence shatters everything we think we know about how stars live together. We are about to journey through 25 of the strangest discoveries ever made about these cosmic mega-families. You will see bizarre physics, witness unexpected stellar behavior, and unlock profound mysteries hidden within the most extreme social gatherings in the universe. How can a dozen suns share a single orbit without tearing each other apart? What kind of planets could possibly survive in that perpetual storm of light and gravity? By the end, you will understand why these rare systems are the ultimate test of our cosmic theories and imagination. What does a sky look like when it is lit by 12 different suns? The story begins not with a flashy telescope image, but with a subtle wobble. Astronomers were studying a star called HD 10180, a sun-like star over 120 light-years away, famous for possibly hosting a rich family of planets. They were meticulously measuring its light, watching for the telltale rhythmic tug of orbiting worlds, but the data refused to be simple. The star's motion was not just a clean set of wobbles from a few planets. It was a chaotic, overlapping mess of gravitational pulls. This radial velocity data painted a picture of an environment far more crowded and intricate than anyone had anticipated. The whispers in the numbers suggested something monumental. This was not merely a planetary system. The gravitational symphony surrounding HD 10180 hinted at a vast hidden architecture. Theorists began to model the possibilities, and the only scenario that fit the bizarre gravitational dance was a staggering one. The evidence pointed toward a hierarchy of celestial bodies so complex it redefined the word system. They were looking at the gravitational fingerprint of not just planets, but of multiple stars influencing each other in a delicate, chaotic balance. The model that finally made sense of the data proposed a stunning reality. HD 10180 was not a solo star with planets. It was likely the brightest member of a system containing up to 12 distinct stellar objects. This was the first strong clue that duodecuple systems were not just fantasy. They could be real, and they were hiding in plain sight, their complexity masquerading as noise in our data. This discovery did more than add a new entry to a catalog. It fundamentally challenged our detection methods. Our tools, designed to find neat planetary orbits around single stars, were almost blind to the gravitational storm of a dozen stars sharing a space. HD 10180 taught us that a quiet stellar neighborhood, by our old definitions, could be a cosmic metropolis in disguise. The stability of such a system seems like an outright physical impossibility. It defies every instinct we have about chaos and order. Yet, the discovery of potential duodecuple systems forced a profound question into the open. How can 12 massive, gravitationally greedy stars possibly share a single cosmic neighborhood without instantly tearing their family apart? The answer lies not in a simple ring of 12 suns, but in a masterpiece of celestial architecture known as a hierarchical system. This is the universe's ingenious solution to managing gravitational chaos. Think of it not as a free-for-all mosh pit of stars, but as a meticulously choreographed ballet performed on multiple stages at once. At the very core, you find the tightest, most intimate dance. Two stars, a binary pair, orbit each other so closely they are practically touching, locked in a furious, fast-paced waltz. This binary pair does not dance alone. It becomes a single gravitational unit, a coupled pair with a combined center of gravity. Now, imagine another identical tight binary pair dancing nearby. These two pairs, each a stable unit, begin to orbit each other at a wider distance. Their dance is slower, more stately, but no less bound. This creates a new, larger gravitational unit, a quartet of stars. This pattern repeats, scaling up like a cosmic set of nesting dolls or a fractal pattern in gravity. A third binary pair might orbit that quartet, or perhaps two quartets slowly circle one another. Each level of the hierarchy operates at a significantly wider separation than the level below it, creating gravitational buffers. The fierce, rapid tugs within a close binary are contained, their violence mostly spent on each other. To a star in the next level out, that furious binary pair appears as a single, slightly wobbly point of mass. This elegant structure is the only way nature can build stability from so many moving parts. It compartmentalizes the chaos. The incredible gravitational forces that would instantly destabilize a flat 12-star ring are instead neatly packaged into manageable, isolated subunits. It is a gravitational pyramid scheme that actually works, each tier providing a stable foundation for the one above it. This hierarchical dance is so delicate that even a slight nudge from a passing star could unravel the entire grand design over millions of years. Their very existence is a testament to a quiet, undisturbed corner of the galaxy, a place where this most fragile of cosmic ballets has been allowed to continue its performance for eons. This hierarchical dance leads to an even stranger revelation about the family members themselves. Within a single duodecuple system, you can find a stellar menagerie of utterly different stars. Picture the hottest, most massive blue-white giants, stars that live fast and die young in spectacular supernova. Now, right alongside them in the same gravitational family, imagine tiny, cool red dwarfs so faint and long-lived they will shine for trillions of years. These stars are not just different sizes, they are different species with lifetimes and destinies separated by cosmic chasms. Even more bizarrely, their ages can be wildly mismatched. Some stars in the group might be youthful infants, only a few million years old, blazing with energy. Others could be ancient relics, billions of years older, quietly burning through their later life stages. This is not what our standard star formation story predicts. The classic model says stars are born together from a single collapsing cloud of gas and dust. They are siblings sharing the same chemical composition and the same birthday. A duodecuple system with this extreme variety shatters that simple narrative. It forces astronomers to consider two radical possibilities. The first is that these systems are cosmic adoption agencies, perhaps a small, stable core of stars formed together in one cloud. Over eons, as this family drifted through the galaxy, its complex gravity acted like a net, capturing lone wandering stars or even snagging smaller, pre-existing binary pairs that passed too close. The system grows not by birth but by acquisition, building its dozen members through a slow process of gravitational kidnapping. This would naturally explain the different ages and types, as the adopted stars came from entirely different origins and times. The second, even more mind-bending possibility is that they all did form together, but from a natal cloud of such staggering size and complexity that it could birth a dozen stars with radically different properties simultaneously. Imagine a cloud so vast and turbulent that pockets within it collapse at different times and under different conditions, some creating behemoths, others creating dwarfs, all before the cloud fully dissipates. This would be star formation on a scale and diversity we have never witnessed. Either scenario rewrites the rules. A duodecuple system is not a simple family portrait. It is a collage, a patchwork of stellar lives and histories forced into a shared, precarious orbit by the universe's most patient and powerful sculptor, gravity. The chaotic gravitational ballet within these systems holds a dark and violent secret. A duodecuple star system is not just a fragile family, it can also become a factory for cosmic fugitives, creating what astronomers call hypervelocity runaway stars. The sheer number of bodies and the complex, overlapping orbits within the hierarchy create a perfect environment for a gravitational slingshot of catastrophic power. Picture a close encounter between two of the binary pairs in their wider orbit. As they swing past each other, their gravity acts like a whip, transferring an immense amount of energy. If the timing and angles are just right, one star, often the lightest member of a tight binary, can be ripped from its partner and catapulted away. It is not a gentle push. This is a violent ejection, accelerating the star to speeds exceeding 1 million miles per hour, fast enough to escape not just its family, but the gravitational pull of the entire Milky Way galaxy. We have observed these solitary, blazing projectiles streaking through intergalactic space, stars on a one-way trip into the cosmic void. For years, their origin was a mystery, often blamed on the supermassive black hole at our galaxy's center. But increasingly, the evidence points to a more local, yet equally dramatic birthplace. Many runaway stars, when traced back along their paths, do not lead to the galactic core. Instead, their trajectories point back to dense, young star clusters. These clusters are now seen in a new light. They are not just random collections of stars, but potentially the degraded remnants of systems that were once far more complex. A duodecuple system, after a particularly violent ejection event, would lose members and its delicate hierarchy could collapse into a simpler, tighter cluster. The runaway star is the bullet, and the cluster is the spent shell casing, evidence of a gravitational gunshot that occurred millions of years ago. So the next time astronomers spot a lonely star racing across the galaxy, they might be looking at a survivor, a refugee ejected from the most extreme and unstable family home the universe can build. The gravitational chaos of a dozen suns creates a sky of perpetual, unpredictable motion, and this translates directly into a light show of impossible complexity. For any observer, whether a distant astronomer or a hypothetical planet within the system, the combined light from these stars does not shine with a steady glow. It flickers, dips, and surges in a pattern so intricate it defies long-term prediction. In a simple binary system, eclipses are clockwork. One star passes in front of the other at regular, calculable intervals, creating a clean, repeating dip in the total brightness. But introduce a third star and the predictability begins to fray. Now introduce 11 more. In a duodecuple hierarchy, eclipses and transits are not orderly events. They are constant, overlapping accidents of alignment. At any given moment, one of the close binary pairs might be eclipsing itself, while simultaneously, one of the wider orbiting pairs is transiting in front of a third stellar group from our line of sight. The light curve, the graph of the system's brightness over time, does not look like a neat set of repeating trenches. It resembles the scribble of a seismograph during a major earthquake, a frantic, jagged line with dips within dips and brightenings that appear out of sequence. A sudden brightening could occur if two stars align from our perspective, their light combining in a lens-like effect called microlensing, only to be followed milliseconds later by a deep dip as another star passes behind a companion. This chaotic flickering poses perhaps the greatest practical challenge for astronomers. Our primary method for finding exoplanets is the transit technique, watching for the tiny, periodic dimming of a star's light as a planet passes in front of it. In the storm of a duodecuple system, that signal is like trying to hear a single, consistent heartbeat in the middle of a roaring heavy metal concert. The planet's faint transit dip is buried under colossal, random dips caused by stars eclipsing other stars. Even if you could somehow isolate it, the planet's own orbit would be so gravitationally tortured by a dozen competing pulls that its transits would never repeat on a reliable schedule. Characterizing such a world, determining its atmosphere or temperature, becomes a task of statistical guesswork, sifting for a coherent whisper in a hurricane of stellar noise. This light curve chaos is the system's signature, a fingerprint of unimaginable complexity written in photons, telling us that here, the very heavens refuse to keep a steady time. Amidst this gravitational storm, planets do exist, but they are nothing like the orderly worlds of our solar system. In multi-star systems, astronomers have found exoplanets following paths of pure celestial madness, orbiting at severe, tilted angles or tracing chaotic loops around not one star but the entire stellar group. Imagine a planet whose orbit is perpendicular to the orbital plane of its host stars, a world that loops over the poles of its suns instead of circling their equators. This is not science fiction, it is a documented reality in systems like Kepler 413b, a planet in a binary star system whose orbital tilt wobbles wildly over just 11 years. In a duodecuple system, this effect would be magnified to an unimaginable degree. The constant, competing tugs from a dozen different gravitational sources act like invisible hands, perpetually nudging and warping a planet's path. A planet might form in a relatively stable orbit around one tight binary pair, only to have its trajectory radically altered over millennia by a slow, sweeping pass from another stellar quartet in the wider hierarchy. The result can be a world on a roller coaster ride through its own solar system, its orbit changing shape and orientation over cosmic timescales. This leads to seasons of absurd extremity. On such a planet, a summer might last for decades, with one or multiple suns blazing overhead continuously, followed by a century-long winter of profound darkness as the world's tilted path carries it into a prolonged celestial shadow. The very concept of a year loses meaning as the orbital period itself is not constant. For any large moons orbiting such a planet, the environment is even more unstable. They would be tugged not only by their planet, but by the variable gravity of the stellar family, likely leading to intense tidal heating and geological chaos. This shatters the classic idea of a habitable zone, that narrow band where liquid water can exist. A planet might pass through the zone, but its wildly varying distance and exposure to different combinations of stellar light would create a climate of violent, unpredictable swings. Life as we understand it would face a challenge beyond any other, needing to survive not just seasonal change but entire orbital reconfigurations. The existence of planets in these systems proves that worlds can form in the most hostile of nurseries, but their fates are written by the relentless and chaotic gravity of a dozen suns. The chaotic orbital dynamics are only half the story. Inside a duodecuple system, the space between the stars is not empty or peaceful. It is a battleground filled with a perpetual storm of supersonic winds. Every star, from the largest blue giant to the smallest red dwarf, constantly blows a stream of charged particles out into space, a stellar wind. In our quiet solar system, the solar wind flows out relatively unimpeded until it meets the thin gas of interstellar space. But in a system with 12 suns, these winds have no chance to escape. They slam into each other at speeds exceeding 1 million miles per hour. When the hurricane-force wind from a hot, massive star collides with the gentler breeze from a cooler dwarf, the result is a titanic shock front. The particles in these winds, mostly protons and electrons, are violently compressed and heated at these collision boundaries. The temperatures in these shock zones can soar to tens of millions of degrees, hotter than the core of most stars. At these insane temperatures, the gas is no longer a simple wind. It becomes a seething, magnetized plasma that glows not in visible light but in high-energy X-rays. If our eyes could see X-rays, a duodecuple system would not look like a collection of tranquil points of light. It would resemble a tangled, glowing web of furious filaments and bubbles, a constantly shifting map of where these supersonic winds are warring with each other. This interstellar weather creates regions of intense radiation pressure and magnetic chaos that can stretch for billions of miles, filling the spaces between the stellar orbits. For any planets caught within this environment, the effects are catastrophic. Their atmospheres would be relentlessly sandblasted and eroded by this endless particle storm. The constant barrage of X-rays would sterilize surfaces and shred complex molecules. This transforms the entire concept of a habitable zone yet again. A planet might orbit at the perfect distance for liquid water, but if it lies in the crossfire between two colliding stellar winds, its atmosphere could be stripped away in a geological blink. The system is alive with an invisible violence, a roaring cacophony of energy that we can only perceive by tuning our telescopes to the most extreme wavelengths of the electromagnetic spectrum. This violent windstorm of colliding particles might be the most obvious chaos, but a deeper, more subtle mystery hides in the very spin of the stars themselves. In many multi-star systems, astronomers have uncovered a strange and unexpected order. The rotational axes of the stars, the imaginary lines around which they spin like tops, are not pointing in random directions. They are aligned. Multiple suns, separated by vast distances in their complex dance, are spinning in the same orientation, as if choreographed by a cosmic director. This discovery is profoundly counterintuitive, given the gravitational slingshots, close encounters, and chaotic dynamics we have described. You would expect these stars to be tumbling wildly, their spins knocked askew by billions of years of gravitational jostling. The fact that they are not suggests a powerful organizing principle that has survived the chaos. There are two leading theories for this eerie synchronization, each telling a different story about the system's birth and life. The first theory points to a shared origin story of stunning coherence. Imagine the system's natal cloud, a colossal sphere of gas and dust light years across. Before it collapsed, this entire cloud was slowly rotating, possessing a single, unified angular momentum. As gravity caused it to fragment into a dozen separate clumps that would become stars, that original spin was conserved. Each fragment inherited a piece of that initial rotation, like children inheriting their parents' eye color. If the fragmentation process was relatively gentle and orderly, the resulting stars would naturally spin with their axes aligned to that original cloud's rotation. This would mean the aligned spins are a fossil, a direct imprint of the system's first moments, preserved for billions of years. The second theory is more dramatic and speaks to the system's long, turbulent history. It suggests the stars may not have been born aligned. Instead, over eons, the same complex gravitational interactions that create chaos also have a smoothing, averaging effect. Through a process called gravitational torquing, the persistent tugs between the stars in their hierarchical orbits can very slowly work to align their spins, much like the Moon's gravity has aligned Earth's rotation with its orbit. In this scenario, the alignment is not a birthmark but a tattoo, acquired through a long and violent life shared in close quarters. It is the system finding a stable, low-energy configuration after an adolescence of turmoil. Determining which theory is correct for a given system is like cosmic detective work. If the alignment is pristine and perfect, it favors the quiet birth theory. If the alignment is rough or only present in some of the stars, it points to the later gravitational sculpting. For a duodecuple system, the answer could be a mixture of both, a record written in spin that tells the story of a calm birth followed by an epic, dynamic lifetime. This alignment is a quiet whisper of order in the maelstrom, a hint that even the most complex families in the universe can find a strange and beautiful symmetry. The aligned spins of the stars are just one piece of a much larger puzzle of order and chaos. To find another, we must look at the very material from which planets are born, the swirling disks of dust and gas that surround young stars. In a normal, single-star system, this protoplanetary disk is a flat, calm expanse, a celestial construction site where dust grains gently collide and stick together, building planets over millions of years. In a duodecuple system, this serene nursery is replaced by a scene of pure gravitational anarchy. The disk, if it can even form coherently, is subjected to a relentless barrage of tugs from a dozen different gravitational masters. Each passing star in the complex hierarchy acts like a cosmic plow, carving gaps, shearing edges, and warping the disk into bizarre, pretzel-like shapes. Instead of a smooth, continuous ring, the disk becomes a collection of clumpy, asymmetric arcs and spirals, a dust cloud in perpetual turmoil. The gentle collisions needed for planet formation are replaced by violent, high-speed impacts that shatter growing planetesimals back into dust. This relentless stirring prevents the calm accretion required to build rocky worlds like Earth. It scatters the building blocks, either flinging them into the central stars or ejecting them into the dark of interstellar space. What remains is not a planet factory, but a chaotic debris field, a testament to a failed formation process. Even after any planets have formed, the chaos does not end. The same gravitational forces that disrupted the protoplanetary disk continue to act on the leftover debris, the comets, asteroids, and icy bodies. In our solar system, the Kuiper belt and Oort cloud are relatively stable, distant reservoirs. In a duodecuple system, these debris disks are violently stirred. A passing star can yank thousands of comets from their stable orbits, sending them screaming inward in catastrophic showers that would last for millennia, pummeling any existing planets. This means a world in such a system faces a permanent, elevated threat of extinction-level impacts, its skies never truly clear of incoming celestial artillery. The disks we might detect around these stellar families are not signs of calm maturity, but scars of a violent and ongoing gravitational war where the peaceful process of building worlds is an impossible dream. The gravitational turmoil of a dozen suns breeds a specific and spectacular kind of stellar violence, the cataclysmic variable. This is a binary pair locked in a deadly embrace, consisting of a white dwarf, the super-dense corpse of a sun-like star, and a normal companion star, often a red dwarf. The white dwarf's immense gravity acts like a cosmic vacuum, relentlessly stealing hydrogen gas from its living partner. This stolen gas doesn't just fall onto the white dwarf's surface. It accumulates in a searing hot, pressurized layer. When the temperature and pressure at the base of this stolen atmosphere cross a critical threshold, something terrifying happens. The accumulated hydrogen undergoes runaway nuclear fusion in a sudden, titanic thermonuclear explosion. From our vantage point, the star appears to go nova, increasing its brightness by 10,000 to 1,000,000 times in just hours before slowly fading over weeks or months. In an isolated part of the galaxy, such events are rare, separated by centuries or millennia. But within the crowded stellar metropolis of a duodecuple system, everything changes. The sheer density of stars, all moving in their complex hierarchical dance, dramatically increases the chances of close encounters and even direct collisions. A lone red dwarf drifting through the inner lanes of the system has a far higher probability of being gravitationally captured by a white dwarf, or of a pre-existing binary pair being nudged into a tighter, more destructive orbit. Think of it as a celestial traffic jam where fender benders are not mere inconveniences, but events that forge new, volatile relationships. This means the rate of creating these deadly binary pairs is likely much higher than in the quiet galactic suburbs. Consequently, the nova eruption rate could be exponentially greater. An observer in such a system might not witness a rare, once-in-a-civilization stellar explosion, but a recurring celestial fireworks show. Nova could erupt every few decades or even years, each blast flooding the system with intense ultraviolet light and X-rays, and hurling shells of ejected material at thousands of miles per second. This constant bombardment would sterilize any nascent life and reshape the chemistry of any remaining protoplanetary disks. The duodecuple environment doesn't just host stars, it actively forges the instruments of their destruction, turning stellar graveyards into factories for periodic, universe-shaking detonations. These periodic novas are mere firecrackers compared to the true cosmic bombs that have likely already detonated within these stellar families. The most massive stars in a duodecuple system, the blue giants, live for only a few million years before ending their lives in a supernova, the most powerful explosion in the universe. In a system this crowded, such an event is not a quiet death in isolation. It is a cataclysm that threatens to tear the entire family apart, yet some of these systems survive. The key to their survival, and a profound discovery, is written in the peculiar, often lopsided orbits of the remaining stars. When a giant star goes supernova, the explosion is rarely perfectly symmetrical. Imagine a balloon bursting. If one side is slightly weaker, the balloon doesn't just expand evenly, it jets away in one direction. A supernova does the same thing on a stellar scale. This asymmetry gives the newly formed stellar corpse either an ultra-dense neutron star or a black hole a tremendous kick, launching it through space at speeds that can exceed 1 million miles per hour. In a simple binary pair, this kick often sends the neutron star flying away forever, breaking the bond. But in the intricate web of a Duodecuple hierarchy, the story is more complex. The exploding star is not just bound to one partner, it is gravitationally tied to an entire family. The violent kick does not necessarily mean escape. Instead, the neutron star or black hole might be sent careening on a wild, elliptical path within the system's gravitational well. The orbits of all the other stars, feeling this sudden, lopsided loss of mass and the rocket-like effect of the kick, are permanently scarred. They are jostled, tilted, and stretched into new, often eccentric configurations. Astronomers can now read these orbits like a forensic report. By meticulously modeling the current motions of the 11 surviving stars, they can run the gravitational clock backwards. They search for the one arrangement, the one explosive event, that would have transformed a once more orderly set of orbits into the strange, skewed dance they observe today. Finding a neutron star or black hole still loosely bound to the group is the ultimate evidence. It means the supernova, despite its unimaginable violence, was not powerful enough to completely sever the gravitational ties that had bound that star to its siblings for millions of years. The system, though battered and reconfigured, endured. It tells us these families are not just fragile, they are resilient, surviving stellar deaths that would shatter lesser arrangements. The ghost of that ancient explosion still haunts the orbits of the living, a permanent tremor in their celestial paths. The supernova's ghostly fingerprint on stellar orbits is just one form of celestial choreography. Another, far more delicate dance might be hiding within the gravitational equations, the possibility of a Trojan star. This idea borrows a concept from our own solar system, from the stable points in space known as Lagrange points. In the simple system of the Sun and Jupiter, there are 5 points where the gravitational pull of the two large bodies and the centrifugal force of a smaller object perfectly balance. 2 of these points, known as L4 and L5, lie along Jupiter's orbit, one leading the planet and one trailing it by 60 degrees. Here, thousands of asteroids, called Trojan asteroids, orbit the Sun in stable harmony, forever locked in Jupiter's gravitational embrace. Now scale this idea up dramatically. Instead of the Sun and Jupiter, picture a massive binary star pair, 2 suns orbiting each other. Their combined gravity creates a similar set of stable Lagrange points in their joint orbit around their common center of mass. The astonishing theoretical discovery is this: in the right configuration, one of these stable points could be occupied not by a tiny asteroid, but by an entire star. A third star, significantly less massive than the binary pair, could potentially orbit at that leading or trailing Lagrange point, forever holding its position relative to its 2 massive siblings. This would be a true Trojan star, a stellar participant in a gravitational ballet of perfect balance. The conditions for this are incredibly strict. The mass ratios have to be just right, and the orbits must be nearly circular to maintain stability. Any significant gravitational nudge from another member of the system could knock the Trojan star out of its delicate equilibrium, sending it spiraling into a new, chaotic orbit within the hierarchy. So, could such a configuration exist in a system of 12 bodies? The mathematics suggests it is possible, but it would be a fleeting miracle of celestial engineering. In a duodecuple hierarchy, every star is constantly feeling the pull of many others, not just one binary pair. The gravitational noise is immense. A Trojan configuration might form temporarily, a chance alignment during the system's chaotic early days, but it would be highly vulnerable. The gentle, persistent tugs from the other 9 or 10 stars in the wider family would act like a constant vibration on a finely tuned instrument, almost certainly destabilizing the perfect balance over time. Finding such an arrangement would be like discovering a single, perfectly symmetrical snowflake surviving in a hurricane. It would be a breathtaking snapshot of transient order, a brief moment where the universe's chaos paused to create a perfect gravitational sculpture before the endless dance resumed its wild, unpredictable rhythm. The fragile gravitational ballet leaves a permanent chemical signature on the stars themselves. When astronomers point their spectrographs at the individual members of a duodecuple system, they do more than measure their motion. They perform a cosmic blood test, analyzing the precise chemical composition of each star's atmosphere. The results are often deeply puzzling. One star might show a bizarre overabundance of lithium, an element normally destroyed early in a star's life. Another might be strangely enriched with heavy elements like barium or europium, metals usually forged only in the violent hearts of supernova or through rare nuclear processes. These peculiar chemical abundances are like finding different family recipes in a shared kitchen, hinting at a history of exotic exchanges. The first clue comes from the system's hierarchical structure. In a tight binary pair, if one star evolves faster and swells into a giant, its outer atmosphere can literally spill over onto its companion. This process, called mass transfer, is a stellar blood transfusion. The receiving star gains not just hydrogen fuel, but all the chemically processed material from the donor's interior, including elements like lithium that the donor created or preserved. The receiving star's atmosphere becomes polluted with the donor's nuclear history, a record of a deep cosmic intimacy. But in a system of 12, the source of pollution might be far more dramatic. Consider a past supernova from one of the massive members we discussed earlier. That explosion would have seeded the entire local environment with a cloud of freshly synthesized heavy elements: iron, gold, uranium. The other stars, especially the younger ones still surrounded by accretion disks, would have literally formed from or swept up this supernova debris. Their atmospheres would carry the unmistakable fingerprint of that ancient stellar death, making them chemically enriched in a way a star born in isolation could never be. This turns the entire system into a layered archaeological site. The oldest stars might show the pristine chemistry of the original birth cloud. Stars of intermediate age could show the pollution from that first supernova. And the youngest stars, or those locked in tight binaries, might show the strange signatures of ongoing mass transfer. By reading these chemical stories, astronomers can piece together a timeline of catastrophic events and intimate exchanges that shaped this stellar family over billions of years, a history written not in stone, but in the elemental makeup of 12 burning suns. The chemical history locked within each star is a story we can only read because the system exists today in a state we can observe. But predicting where it will go from here or how it formed in the first place pushes our greatest computers to their absolute limits. This is the domain of n-body simulations, the digital laboratories where we try to recreate the gravitational dance of a dozen suns. The discovery from these simulations is humbling and profound. The long-term fate of a duodecuple system is fundamentally, mathematically unknowable. It is not just complex, it is chaotic in the purest scientific sense. To run such a simulation, astrophysicists must define the starting point. They input the estimated masses, positions, and velocities of 12 hypothetical stars arranged in a hierarchical pattern. Then they unleash the laws of gravity and set the digital clock running. The supercomputer calculates the gravitational force between every single pair of stars, updates their velocities and positions by a tiny fraction of a second, and then does it again, trillions upon trillions of times to model just a few million years of cosmic evolution. Even with this staggering computational power, a clear truth emerges. The tiniest, most imperceptible change in the starting conditions, shifting one star by the width of an atom, or altering its speed by less than a millimeter per second, leads to a completely different future. Over thousands of orbits, that microscopic difference is amplified by countless gravitational interactions until the two simulated systems diverge utterly. In one version, a star might be ejected after 2 million years. In the other, that same star remains bound, but a different one is flung into the void. The stable hierarchy might hold for eons in one simulation, while in another it unravels into a chaotic scrum within a fraction of that time. This is the famous butterfly effect applied to stellar dynamics. It means that no matter how precisely we measure a real duodecuple system today, we can never know exactly what it looked like a million years ago, nor what it will become a million years from now. Our measurements will always have some minuscule error, and that error grows exponentially in the simulation, erasing any predictive power over cosmic timescales. Each real system is therefore a unique, unrepeatable cosmic experiment. Its current configuration is just a single frame pulled from an infinite reel of possible films, all starting from nearly identical points. The simulations don't give us a definitive answer. Instead, they show us a breathtaking spectrum of possibilities, a reminder that in the realm of 12 stars, the universe reserves the right to write its own unpredictable story. Gravitational stretching in such a crowded system does far more than warp orbits. The same relentless tidal forces that keep our moon locked facing Earth operate here on a monstrous system-wide scale. In a duodecuple hierarchy, these forces can create chains of tidal locking that bind multiple stars together in a fixed gravitational embrace. Imagine a close binary pair, so tightly bound that each star has permanently locked one face toward the other, just as our moon does to Earth. Now picture that entire locked binary pair acting as a single unit, being in a wider orbit with another stellar pair. The gravitational pull between these two units can be so persistent and rhythmic that it forces the entire binary pair to synchronize its rotation with its orbital period around the other pair. We get a locked pair orbiting another locked pair, a cosmic gear system where multiple rotations are synchronized across vast distances. This tidal locking isn't a gentle process. It works by gravitational friction. As a star rotates, its bulge of mass, raised by a companion's gravity, tries to stay aligned with that companion. If the star's spin is too fast or too slow, the bulge is constantly being dragged around, deforming the star's interior. This internal flexing generates immense heat through friction, a process called tidal heating. On a moon like Jupiter's Io, this heat drives the most violent volcanic activity in the solar system. Now scale that up to a star. The internal heating from being tidally stressed by not one, but several companions can be staggering. It churns the stellar interior, altering convection patterns and potentially mixing fresh hydrogen fuel into the core. For a star, this is a profound intervention. By stirring its nuclear furnace, tidal heating can actually extend the star's lifespan, allowing it to burn its fuel more slowly and efficiently. Conversely, for certain types of stars, this extra internal churning could intensify magnetic dynamos, leading to hyperactive star spots, monstrous solar flares, and coronae that blaze with X-rays far beyond their years. A star's activity cycle, its version of an 11-year solar cycle, could be thrown into chaos, becoming erratic and violent. This means a star in a duodecuple system does not live its life in isolation. Its very nuclear heart rate, its magnetic personality, and its ultimate lifespan are not solely determined by its mass. They are sculpted by the perpetual gravitational massage of its many siblings, a fate no solitary star will ever know. The sheer chaotic potential of a 12-star family forces a deeper question. Is 12 the universe's limit? scientists are now actively searching for the theoretical upper boundary of gravitational complexity, and duodecuple systems stand right at that precipice. The quest is to understand if nature has a fundamental rule against larger families, or if we simply have not found them yet. The answer lies in a brutal mathematical reality known as dynamical stability. Each star added to a system does not just add one more relationship, it adds a web of new gravitational interactions. Think of it like a conversation. With 2 people, there is 1 line of communication. With 3 people, there are 3 possible conversations. With 12 stars, the number of gravitational conversations happening simultaneously is staggering. Each of these interactions is a potential source of chaos, a tiny push or pull that, over millions of orbits, can amplify into an ejection or a collision. Computer models suggest that as you approach 13, 14, or 15 stars, the probability of the entire configuration holding together for even a few million years plummets exponentially. The hierarchical structure, that elegant nesting of binaries, begins to fail. The gravitational buffers between levels break down. A close encounter in the outer tier can now send a shockwave of instability cascading all the way down to the innermost binaries, unraveling the entire delicate architecture in a cosmic chain reaction. This makes systems with 13 or more stars not just rare but likely ephemeral. They might form in the densest stellar nurseries, only to violently disassemble themselves on timescales that are a mere blink in galactic history. Finding a true tridecuple system, one with 13 permanently bound stars, would therefore be a monumental discovery. It would mean our understanding of gravitational stability is incomplete, that there exists an even more ingenious, undiscovered hierarchical pattern that nature can employ. For now, the duodecuple system remains the ultimate test case, the most extreme laboratory we have for pushing the laws of celestial mechanics to their absolute breaking point. Its continued existence is a quiet triumph of order over chaos, a demonstration that even at the very edge of what is possible, gravity can still weave a stable, if impossibly complex, tapestry. This relentless gravitational dance has a voice we are only just beginning to hear. The intricate orbital motions of 12 massive stars do not just bend space, they rhythmically shake the very fabric of the universe, generating ripples known as gravitational waves. Every time a star in a tight binary whips around its partner, or a stellar quartet completes a slow, grand orbit, it broadcasts energy outward as these subtle space-time tremors. For a single duodecuple system, the signal is far too faint, lost in the cosmic noise. But think of the galaxy not as a quiet place, but as a crowded room. Astronomers now theorize that our Milky Way likely hosts a population of these extreme systems, each humming its own unique, low-frequency gravitational tone. Together, they create a collective murmur, a faint but continuous background hum woven from countless chaotic stellar dances. This is the stochastic gravitational wave background, a cosmic symphony of space-time vibrations from all the universe's most energetic events. Until now, we have tuned into the loud, singular crashes, the mergers of black holes and neutron stars detected by observatories like LIGO. The gentle, overlapping hum from sources like duodecuple systems represents an entirely new frequency band, a lower register of the gravitational spectrum. Future space-based observatories like the planned LISA mission are designed specifically to listen for these low-frequency waves. By floating laser-equipped satellites millions of miles apart in space, they will act as the most sensitive microphone ever conceived, capable of detecting the minute stretching of space-time caused by these distant stellar families. Isolating the specific contribution from duodecuple systems will be a monumental challenge, like picking out the sound of a single violin section from a recording of a full orchestra playing in a thunderstorm. Yet, if successful, it would open an entirely new window into the hidden architecture of our galaxy. We would not just see these complex families with light, we would feel their collective rhythm through the vibrations of spacetime itself, confirming their numbers and mapping their distribution in a way traditional astronomy never could. This background hum is the cumulative echo of gravity's most complex choreography, a direct signal from the universe's most extreme social gatherings, waiting for us to finally lean in and listen. The gravitational hum we listen for depends on one critical fact, that the stars are truly bound together. But the cosmos is a master of deception, and some of the most tantalizing duodecuple candidates might be nothing more than breathtaking celestial mirages. This discovery forces a sobering reality check. When we peer into the dense star fields of the Milky Way's spiral arms or globular clusters, our view is flattened into a two-dimensional picture. Stars that appear to be neighbors in the sky, clustered tightly together, could in reality be separated by vast gulfs of space along our line of sight. One star might be 1,000 light-years away, while another that seems right beside it is actually 3,000 light-years farther. From our vantage point, they project onto the same patch of sky, creating the perfect illusion of a bound family. A random, dense cluster of a dozen stars could easily masquerade as a hierarchical system if we only have a snapshot. Untangling this illusion requires the most meticulous detective work in astronomy, a multi-pronged investigation that moves far beyond a simple photograph. The first and most crucial tool is precise astrometry, the science of measuring stellar positions with unbelievable accuracy. Astronomers don't just take one picture, they take them over years and decades. They are looking for the shared motion, the common proper motion, that would prove the stars are traveling together through the galaxy. If all 12 candidates are truly bound, they will move as a unit against the backdrop of more distant stars, like a flock of birds crossing the sky in formation. If, however, their motions are random and divergent, it reveals they are merely strangers passing in the night, their proximity a temporary trick of perspective. The second tool is radial velocity, measuring the Doppler shift of each star's light to determine if they are orbiting a common center of mass. In a true system, the velocities will have a gravitational coherence, a rhythmic pattern that fits a hierarchical model. In an optical illusion, the velocities will be unrelated, telling 12 independent stories. This painstaking work is like listening to a cacophony and trying to pick out a single, complex symphony. It requires ruling out chance alignments with statistical certainty, a process that can take longer than a human lifetime. For every candidate duodecuple system that survives this brutal vetting, its reality becomes that much more extraordinary. It means we are not being fooled by a projection, but are truly witnessing one of the rarest and most fragile structures gravity can build. The cosmic mirage of chance alignments forces us to ask where a real duodecuple system could possibly form and survive. The answer may lie in the most crowded stellar cities in the galaxy, the ancient hearts of globular clusters. These dense, spherical swarms of hundreds of thousands of stars are relics from the galaxy's violent youth. In their ultra-dense cores, stars are packed so tightly that the average distance between them can be less than our solar system's width. Here, stellar interactions are not rare events, they are a constant reality. In this frenetic environment, the complex gravitational choreography of a 12-star system might not be a fragile miracle, but a natural, if temporary, outcome. The theory suggests that the chaotic dance in a globular cluster core could act as a cosmic assembly line for extreme hierarchies. Picture a tight binary pair whizzing through the core. Its combined gravity acts like a net, capturing a third star during a close encounter. This new trio, now a more massive unit, has an even greater chance of capturing a fourth star and then a fifth. Through a stepwise process of gravitational theft and capture over millions of years, a complex hierarchical system could be built from the bottom up, right in the densest stellar neighborhood imaginable. This assembly process would be incredibly dynamic and violent. The system would not form in quiet isolation, but would be constantly bombarded, its outer members stripped away or replaced by new captures from the passing stellar traffic. Such a system would live a life of perpetual gravitational negotiation, its structure evolving in real time. The ultimate fate of these cluster-born mega-families is what makes them so important to the life of the cluster itself. They become gravitational engines. The complex interactions within the hierarchy can fling stars out at high speeds, not just as runaway stars into the galactic field, but also as energetic projectiles that heat the core of the cluster, preventing it from collapsing further under its own gravity. Even more dramatically, the tightest inner binaries could be driven to merge, creating exotic blue straggler stars that appear unnaturally young, or even triggering cataclysmic events. A merger of two white dwarfs could produce a Type 1, a supernova, a titanic explosion that would scatter heavy elements and energy throughout the ancient cluster. The Duodecuple system, in this view, is not a passive resident of the cluster core. It is an active, short-lived agent of change, a temporary gravitational vortex that processes stars, releases energy, and forges strange new objects before the relentless stellar traffic of the core inevitably tears it apart. Finding one in a globular cluster today would be like finding the still smoking gun at the scene of a cosmic crime, evidence of the incredibly dynamic processes that shape these ancient stellar metropolises. A mysterious, repeating radio pulse from deep space could be the signature of a stellar family tearing itself apart. Among the most perplexing signals astronomers have ever detected are fast radio bursts, flashes of radio energy so powerful they outshine entire galaxies for a few milliseconds. Most appear as one-off events, cosmic lightning strikes with no obvious cause. But a small, crucial subset are repeaters, firing off bursts at irregular intervals from the same patch of sky. Their source has remained one of astronomy's greatest mysteries. Now, theorists are asking a radical question. Could the engine behind some of these repeating signals be the unimaginable physics of a duodecuple star system? The sheer density of exotic objects and the scale of magnetic and gravitational energy present in such a family make it a prime suspect. One compelling model involves a neutron star, the super-dense remnant of a past supernova, still bound to the system. If this neutron star is a magnetar, a variety with a magnetic field 1,000 trillion times stronger than Earth's, it possesses unimaginable stored energy. In the chaotic gravitational environment of a dozen stars, such a magnetar could be repeatedly jostled. A close pass from another stellar member could trigger a starquake on its crust, a seismic event that twists its colossal magnetic field lines, releasing a catastrophic burst of radio energy in a process akin to a cosmic short circuit. This could explain a single, powerful burst, but for a repeater, we need a cycle. Imagine that magnetar is not alone. It is in a tight, eccentric orbit with another star, perhaps a white dwarf or a main sequence companion. As they swing close together, the companion's gravity could periodically stress the magnetar's crust at the same orbital phase, triggering quakes and bursts on a semi-regular schedule. The duodecuple environment adds another layer of chaos, as the orbit of this deadly binary pair itself is perturbed by the other stars, explaining why the repetition might be erratic, sometimes going quiet for months before firing again. Another model skips the starquakes entirely and looks to a lighthouse effect, a neutron star's beam of radio emission, which we detect as a pulsar's steady tick, could be sweeping past Earth only under very specific conditions. If the neutron star's spin axis is slowly wobbling or precessing due to gravitational torques from its many stellar siblings, its lighthouse beam might only intersect our line of sight intermittently. Each time it flashes across Earth, we would see a brief, bright pulse of radio waves. The timing of these flashes would depend on the complex precession cycle, potentially creating a repeating pattern over years or decades that would be incredibly difficult to decode because it is driven by the gravitational chatter of a dozen suns. While a lone neutron star in a quiet part of the galaxy could produce a steady pulse, the unique stresses of a crowded stellar family are what might forge the strange, stuttering, and hyper-energetic repeaters we struggle to explain. Finding a fast radio burst source localized to a known region of extreme stellar density, perhaps near a globular cluster core, would be a major clue that we are hearing the final, furious transmissions from a star system living on the gravitational edge. The silent graveyard of a duodecuple system is where stellar life and death share the same orbit. After billions of years, the most massive members of the family have already burned through their fuel and died, leaving behind their compact, ghostly remnants. What remains is a morbidly fascinating cosmic cemetery, a hierarchy now populated by a mix of the living and the dead. Normal, shining stars continue their dance alongside the invisible corpses of their siblings, white dwarfs, neutron stars, and even black holes, all still bound by the gravity that once nurtured them. This creates a gravitational environment unlike any other, where the living and the dead interact with profound and detectable consequences. The most subtle of these effects is a timing anomaly, a tiny hiccup in the expected rhythm of the system. Consider a surviving pulsar, a rapidly spinning neutron star that beams radio waves at us with the precision of a cosmic atomic clock. Its steady tick, tick, tick should be unerringly regular. But in this graveyard, it is not alone. As the pulsar orbits through the system, it passes near the immense, invisible gravity well of a stellar mass black hole, a corpse from a past supernova. According to Einstein's theory, time itself slows down in a strong gravitational field. So, from our distant perspective, the pulsar's clock appears to slow down slightly as it swings close to the black hole, its ticks arriving a fraction of a millisecond later than predicted. Then, as it moves away, the ticks speed up again. This is not science fiction. It is a measurable effect called gravitational time dilation. And in a system with multiple dead remnants, these timing anomalies become a complex fingerprint. Astronomers would see the pulsar's rhythm not just perturbed by one object, but warped and twisted by the combined, shifting gravity of several invisible companions, a white dwarf here, a neutron star there, a black hole farther out. Decoding this pattern is like listening to a ghostly symphony. Each anomaly in the pulsar's tick reveals the mass and position of an unseen grave. By mapping these gravitational whispers, we could theoretically chart the entire graveyard, building a map of the invisible architecture shaped by stellar death. It is a direct observation of general relativity in its most extreme playground, a place where the ghosts of dead stars leave ripples not just in space but in the very flow of time. A duodecuple system is more than a family of stars, it is a living fossil. The intricate, chaotic dance of its 12 members holds a hidden record, a precise memory of where and when this stellar family was born. This makes them extraordinary tools for galactic archaeology, the science of reconstructing our galaxy's violent history by studying the motions of its oldest inhabitants. Most stars in the Milky Way's disk have had their orbits smoothed and randomized over billions of years by countless gravitational encounters, like pebbles tumbled in a stream until their sharp edges are gone. But a bound system of 12 stars is different. Its immense collective gravity acts as a protective bubble. While individual stars within the hierarchy jostle, the system's center of mass, the point around which all 12 orbit, moves through the galaxy with a singular, preserved trajectory. This trajectory is a cosmic birth certificate. By measuring the system's precise speed and direction through the Milky Way today, astronomers can run the galactic clock backwards. They account for the known gravitational pull of the galaxy's spiral arms, its central bar, and its dark matter halo. They trace the duodecuple system's path in reverse, winding the film back through 5, 8, even 10 billion years. The end point of that rewind is its birthplace. Often, the trail does not lead to a quiet region of the galactic disk. It points instead to a specific, ancient star-forming complex that has long since dissipated, or even more dramatically, to a place far outside the Milky Way's current boundaries. The most thrilling discovery is when a system's kinematic fingerprint, its specific combination of velocity and position, matches that of a known stellar stream. These streams are the ghostly remains of small dwarf galaxies that were torn apart and consumed by the Milky Way's gravity billions of years ago. If a duodecuple system's motion aligns with one of these galactic fossils, it means something profound. This incredibly complex family did not form in the Milky Way at all. It was forged in the heart of a separate, smaller galaxy that was later devoured. The system survived the cataclysmic merger intact, a complete celestial ecosystem that was swallowed whole and now orbits within our galaxy as a captured relic. Its very existence and its preserved motion provides a timestamp for that ancient act of galactic cannibalism. Studying such a system is like finding a perfectly preserved artifact from a lost civilization, with its original language and customs intact, allowing us to understand not just the artifact itself, but the entire culture that created it. Each duodecuple system is therefore a time capsule with two histories locked inside: the chaotic story of its internal gravitational ballet and the epic saga of its journey across the galaxy, a journey that may have begun in a world that no longer exists. A civilization born under 12 suns would see a universe we can scarcely conceive. Their entire science, their philosophy, and their very sense of place in the cosmos would be forged in a crucible of perpetual celestial motion. For us, the sun rises and sets with a predictable rhythm, the seasons follow a reliable cycle, and the night sky offers a fixed map of distant guideposts. For them, predictability is a foreign concept. Their sky is a dynamic, ever-changing canvas where constellations warp and dissolve over a single lifetime. The very idea of a North Star, a fixed celestial pole, would be meaningless. Navigation would not rely on static points of light, but on calculating the complex gravitational harmonies between their moving suns, a mathematics of chaos we are only beginning to understand. Their concept of time would be equally fluid. With no single, dominant day-night cycle, biological and societal rhythms might sync to the overlapping periods of the brightest stellar pairs, or to the rare moments of collective darkness when all suns are below the horizon, events that could be their most sacred holidays. This foundational difference makes the search for extraterrestrial intelligence, or SETI, even more challenging. Our efforts have long assumed a civilization like ours, one that might use regular pulses of light or radio waves, perhaps timed to planetary orbits or the rotation of a single star. But what signal would a duodecuple culture send? Their most natural clock is the gravitational dance itself. A signal might be timed to the complex orbital resonance of their inner binary quartet, or pulsed in a pattern that mirrors the chaotic light curve of their 12 suns. Their beacon might not be a steady tone, but a stuttering, seemingly random sequence that only makes sense if you understand the intricate orbital mechanics of their home. Furthermore, their technological development would be steered by their environment in profound ways. The constant barrage of stellar radiation and gravitational tides would make space travel within their own system a nightmarish challenge, perhaps pushing them to master gravity manipulation or shielding technology far earlier than a species from a quiet system. Their telescopes would be designed not to find distant planets, a near impossible task in their stellar storm, but to map the gravitational waves and magnetic webs that define their immediate reality. If they ever looked outward and tried to signal another star, they might not target sun-like stars at all. They might seek the complex radio fingerprints or gravitational murmurs of other multi-star systems, recognizing them as kin in a universe of simpler solar arrangements. Their message might not be a simple mathematical primer, but a symphony of orbital periods and tidal forces, a shared language of celestial chaos. To receive and understand such a signal, we would need to first learn the complex grammar of their sky to hear the music in what we currently perceive as gravitational noise. It is a humbling thought that our search for cosmic company might be filtered through a single, quiet experience of the universe, while other minds are dancing to a rhythm of 12 different drums. The ultimate test of gravity is not found in a quiet, empty void, but in a crowded, chaotic stellar city. A duodecuple star system, with its intricate web of masses and motions, becomes the most precise natural laboratory we have for probing the deepest predictions of Einstein's theory of general relativity. Within our solar system, we have tested relativity with exquisite accuracy, using the orbit of Mercury or the bending of starlight around our Sun. But these are gentle tests conducted in what physicists call a weak gravitational field. A duodecuple system offers something far more extreme, a strong field regime where gravity is not a gentle curve in space-time, but a violent, twisting force generated by multiple, dense objects moving at incredible speeds. One of the most profound tests comes from orbital precession, the slow, steady rotation of an orbit's orientation over time. Mercury's orbit precesses due to the Sun's gravity warping nearby space, a key confirmation of Einstein's work. In a duodecuple system, this effect is magnified and multiplied into a dizzying dance. Each star's orbit, especially those in the tight inner binaries, is being tugged not just by its immediate partner, but by the combined gravity of all the other stars in the hierarchy. This creates a complex, overlapping precession. The orbit of a tight binary pair will slowly tumble like a spinning coin. That entire binary's path around a second pair will also precess. The result is a cascade of relativistic wobbles, a multi-layered gyroscope in space. Measuring these subtle shifts with extreme precision allows astronomers to check if Einstein's equations still hold when multiple strong gravitational fields are stacked and interacting in ways his theory never had to address directly in our simple solar system. Even more mind-bending are the effects on time itself. General relativity tells us that time flows slower in a stronger gravitational field. On Earth, this is a tiny effect measurable only with atomic clocks. But in a duodecuple system, the differences in gravitational potential are staggering. A neutron star or white dwarf remnant has a surface gravity billions of times stronger than a normal star's. If a pulsar, a ticking neutron star clock, is in a wide orbit with a normal star, their clocks will tick at radically different rates. As they swing through their orbits, the difference in their experienced time will rhythmically increase and decrease. We can detect this by watching the pulsar's radio ticks. When it is deeper in the collective gravitational well of the system, its signals will be delayed, stretched out like a record played too slow. These are not theoretical musings. In a few known binary pulsar systems, these effects are measured, and they match Einstein's predictions perfectly. In a system of 12 bodies with stars and remnants at vastly different gravitational potentials, this time dilation becomes a chorus of out-of-sync metronomes, offering a three-dimensional map of warped space-time that no human-made experiment could ever replicate. Finally, there are the subtle, cumulative perturbations. In Newton's gravity, the pull between two bodies is simple and direct. In Einstein's universe, gravity propagates at the speed of light, and moving masses create additional, subtle effects like frame dragging, where a spinning star literally twists the fabric of spacetime around it. In a calm system, these effects are minuscule. In the gravitational storm of a duodecuple hierarchy, they can accumulate. The spin of one massive star can ever so slightly alter the orbit of another star far away, not through direct pull, but by distorting the space through which that star moves. Detecting this requires tracking the positions and spins of multiple stars over decades, looking for tiny deviations that Newtonian physics cannot explain. It is like trying to measure how the spin of one dancer in a crowded ballroom changes the path of another dancer on the opposite side, not by touch, but by how they each warp the floor beneath their feet. Each of these tests, the precessing orbits, the mismatched clocks, the ghostly perturbations, is a question posed to the universe. By observing how a duodecuple system answers, we are not just learning about 12 strange stars. We are stress testing the very framework of reality, discovering if the rules of gravity, forged in the quiet of our solar neighborhood, still hold true in the cosmos's most riotous and extreme environments. This profound rarity is the final and perhaps most humbling discovery. After exploring 24 layers of gravitational chaos and stellar violence, we arrive at a simple, staggering fact. True, stable duodecuple star systems are almost impossibly scarce in the observable universe. For every one of these celestial mega-families, there are billions upon billions of solitary stars like our Sun or simple binary pairs. Their extreme fragility and the specific, undisturbed conditions required for their formation mean they are cosmic unicorns, fleeting masterpieces of gravitational architecture. This scarcity is not a minor detail. It carries a profound implication for the potential of life. We have walked through the reasons why a planet in such a system faces an apocalyptic gauntlet. The chaotic orbits, the violent stellar winds, the relentless radiation, the unpredictable supernova shocks. It is a recipe for planetary sterilization. The utter rarity of these systems, therefore, whispers a compelling cosmic truth. It suggests that the universe itself, through the cold mathematics of stability and chaos, has already performed a great filtration. By making serene, single-star systems the overwhelming galactic norm, the cosmos has implicitly created vast, quiet neighborhoods where the delicate, long-term processes necessary for life can unfold without constant celestial interruption. Our solar system, with its single, stable star and orderly planetary orbits, is not boring or average. In a cosmos brimming with stellar extremes, from black hole binaries to these chaotic dozen-star families, our quiet corner is the special one. It is the cosmic equivalent of a sheltered valley, protected from the gravitational hurricanes that rage through more crowded stellar metropolises. This does not mean life is impossible in a duodecuple system. The universe is endlessly inventive, but it does mean that if life is a delicate flame, it finds its safest harbor not in the riotous stellar cities, but in the galactic suburbs on worlds orbiting single, gentle suns. The discovery of their rarity ultimately reframes our own place in the universe. We are not inhabitants of a mundane backwater. We are the beneficiaries of a profound cosmic quiet, a stability so vast and common we almost fail to notice how precious it truly is. Their profound scarcity makes each confirmed duodecuple system a priceless treasure. Our journey through 25 strange discoveries has revealed a universe within a universe, a place where gravity writes symphonies of chaos and order on a scale we are only beginning to hear. These systems are not just astronomical curiosities. They are cosmic puzzles that push the very boundaries of astrophysics, forcing us to rewrite the rules of star formation, orbital mechanics, and stellar life and death. They act as natural laboratories, testing Einstein's theories in strong field environments no human experiment could ever replicate. And above all, they are breathtaking reminders of the universe's boundless, often violent diversity. They prove that the cosmos specializes in architectures of unimaginable complexity, hiding them in plain sight, waiting for our curiosity and technology to catch up. From gravitational slingshots creating runaway stars to the ghostly hum of their collective spacetime vibrations, every discovery peels back a layer of a deeper mystery. So, which of these 25 revelations amazed you the most? Was it the idea of a Trojan star locked in gravitational harmony, or the thought of a sky where 12 suns create a light show of perpetual chaos? Share your thoughts in the comments below, and if you crave more journeys to the edges of our understanding, subscribe for deeper dives into the greatest space mysteries.